Greetings, good people. In the last session, I talked about tuning so that we all play the same note, or at least all the people in a particular section are playing the same note. They're all sounding at the same pitch. In this session, I want to talk about harmony. That's to say, playing different notes, but which are harmonious with the other notes which other people in the ensemble are playing. When you play two different notes together, they either sound good or they don't, or something in between. But sometimes when you play two notes together, they sound particularly right, and that's called consonance. We say that those two notes are consonant together. Now, the Western musical scale, la da 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 dee 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 dee. The Western musical scale is a skill which we have all learnt over millennia. The question which I'm going to discuss this afternoon is there actually a physical reason why we find certain combinations of notes particularly tuneful? Is it something we've learnt, or is there actually a physical reason behind it why we find those combinations particularly consonant? So, in order to discover something about this, let's consider the bugle. The bugle is the simplest form of brass instrument. It's a conical tube which flares out at the end. It's got a mouthpiece on the other end, and generally speaking, it's wrapped into a coil to make it suitably short. And the thing about a bugle is that it has no valves or anything else for changing its fundamental pitch. But nevertheless, you can play distinct notes on a bugle. It's all done, so the people who play brass tell me, so it is all done by what is called embouchure. It's the way you hold your lips and you tighten this. I can't do it. I've never played a brass instrument. That's what they all tell me, is by varying the embouchure, you can play different notes. And the bugle actually has a scale which consists of 5 notes. And if we imagine that you're starting on C, if you start on C, then those notes are C, G, C again, E, and G. Now I'm going to play you those notes on my trusty Descant recorder. We have the C, the G, the C, the E, and finally the top bugle note, if you just think about those notes, you may recognize some well-known tunes. Which of course is the end of the last post. And that's how we can remember a fifth. C to G, a perfect fifth. Why are those the notes which actually happen if you blow differently into a bugle? And the answer is because all of those notes have a relationship to the length of the bugle. If you unwind a bugle and consider that as its length from the mouthpiece to the bell, if you take that length, then all of those notes fit into that length. Their wavelength is related to that length. And so the first note, the C which we sound first, goes with two waveforms into that length. 2. It's the second harmonic. This is what we mean by harmonics. Harmonics are pitches which relate, whose wavelength relates to the length of our instrument. And so the C, which you sound as the first note on the bugle, is actually the second harmonic. They don't use the fundamental. So this is the second harmonic. And the next note up, which you get by blowing differently, is and that has 3 waveforms within the same length. And the C has 4 waveforms. It's the 4th harmonic, and therefore it has twice as many as the note an octave lower. 2, 4. Now, the E, fits exactly 5 times into the length of the bugle, and the top's G goes 6 times. So, why are these notes familiar to us? Because people have been blowing into ram's horns and making tubes with mouthpieces and bells for 2.5 millennia. That's why you can train almost anybody to pitch a fifth. Da, 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 da. It's a learned skill, but it's an easily learned skill because there are a huge number of instruments which naturally break on a fifth in that way. So that's why we recognize a relationship between the 5th note of the scale and the fundamental, because it's actually a ratio of frequencies of 3 to 2. It's the 3rd harmonic against the 2nd harmonic. That's why these things sound familiar, and that's why they sound right. 6 centuries before Christ, there was a Greek mathematician called Pythagoras. Now, you probably have heard of Pythagoras because you know all about the fact that the hair on the hippopotamus is equal to the sum of the hairs on the other 2 hides. But Pythagoras also did some work on sound. He studied a Greek instrument which was called the lyre. The lyre has a yoke at the bottom, like that, and strings, generally 5 strings. And what Pythagoras observed was that given everything else, if everything else is equal, if you have the same tension, you have the same material of which the string is made, which was normally gut, and if you have them under the same tension, so if all else is equal, then the longer the string, the lower the note. You halve the length of the string, you double the pitch. So he knew about the fact that different notes had different pitches, and he understood that there was a numerical relationship between a pitch and another pitch, which can be shown on the strings of a lyre because they're of different length. Because of that, he recognized that the G of our scale is actually related to the C by a ratio of 3 to 2. And he noted the fact that that commonly occurs on bugles and things like that, and therefore it's something which we naturally recognize as consonant. And he also noted that people feel that the music is richer when that happens. So he noted that the lyre was tuned in fifths, and you actually tune by pitching a fifth, which people could easily do because they'd heard it on bugles and things like that. Now, the real question which I asked at the beginning is, why do we feel that those intervals, a fifth, why are intervals like the octave and the fifth particularly consonant? Well, the answer lies in what Pythagoras discovered. An octave is a ratio of 2 to 1 in frequency, and a fifth is a ratio of 3 to 2. And what those things have in common is the difference. When two notes sound together, the waveforms interact so that you get both the two notes, the sum, and the difference. And if the difference between the two frequencies is in the ratio of 3 to 2, then the difference frequency has an equivalent of 1. And the same thing is true for an octave. 2 minus 1 is 1. So both those two ratios produce a difference frequency which is the fundamental first harmonic. If you play the second and third harmonics against one another, the difference frequency is the fundamental first harmonic, and that actually, you can hear it if you listen for it very carefully. So that's why we recognize those things as consonant, because when you get the tuning right, and it's a perfect integer ratio between the two frequencies which are being sounded, there's the difference frequency, which is the fundamental first harmonic. I'm going to continue this in part 2.